Welcome to the Explainer. We rely on proofs for, well, pretty much everything, from geometry to rocket science. But have you ever stopped to think, how do we know a proof itself is actually correct? What if there's some tiny hidden flaw in the logic? Today, we're going to dissect the very grammar of our reasoning to see how mathematicians built a system to prove that their proofs are true. So here's our game plan. We're going to start with a crisis that honestly shook mathematics to its foundations. Then we'll see how that forced logicians to put proofs under a microscope, how they untangled the messiest logical knots and discovered a whole universe of different logics. And you're definitely going to want to stick around because the last piece of this puzzle connects everything to the code running on your phone right now.
All right, so let's set the scene. It's the turn of the 20th century. Mathematicians are exploring these wild, incredibly abstract new ideas, but the further they pushed, the more cracks they started to find. Paradoxes were popping up everywhere, and a real, genuine crisis of confidence was starting to take hold.
This became the burning question. You had thinkers like David Hilbert basically sounding the alarm, calling for a new, completely unshakable foundation for all of mathematics. They realized that to trust their conclusions, they had to stop just doing math and start analyzing the very process of reasoning itself. The way forward was to completely change how they thought about proofs. They had to stop treating them like persuasive essays, full of natural language and intuition. The goal was to treat them like formal mathematical objects, to create a symbolic language so precise, so unambiguous, that its logic could be checked by a machine. No room for human error, at all. So, this whole quest for absolute certainty gave birth to an entirely new field. One dedicated to putting proofs themselves under the microscope. And that field is called proof theory. A brilliant logician named Gardensen was really the pioneer here, back in the 1930s. His whole goal was to dissect the anatomy of a logical argument, step by painstaking step. He came up with this amazing system he called the sequent calculus. Now, the easiest way to think about it is like a grammar book, but for pure reason. It defines the absolute, fundamental, rock-solid rules for how you get from a bunch of assumptions to a logical conclusion. But here's where it gets really clever. Gardensen's system wasn't just about describing proofs. It gave him the tools to take them apart, analyze them, and simplify them in a way no one had ever done before. He was basically hunting for the tangled knots in our logic. And he zeroed in on one particular rule he called the cut. A cut is really just a logical shortcut. You know how if you've already proven some smaller intermediate fact, a lemma, you can just use it in a bigger proof? That's a cut. It's incredibly useful for sure, but it can also hide a lot of complexity. And this led to Gardensen's absolute masterpiece, the cut elimination theorem. What he proved was that any proof that uses these cut shortcuts can be systematically transformed into a brand new proof of the exact same thing that uses no cuts at all. So why does that matter so much? Getting rid of the cuts turns a tangled, roundabout proof into a clean, straight path from your starting point to your conclusion. It makes everything transparent. It guarantees that nothing is hidden and that the logic is solid from the ground up, which is an absolutely critical step if you want to prove that an entire system of math is consistent. So once logicians had these powerful new tools for analyzing proofs, they started looking at different systems of reasoning. And what they found was, well, it was pretty profound. They discovered there isn't just one single universal logic with a capital L. It's more like a vast universe of different logics, each with its own set of rules and axioms. This completely blew open the doors for new formal systems in fields like AI, database theory, even linguistics. For example, think about classical logic, the one we're all used to. It assumes any statement is either true or false, period. But then you have something like intuitionistic logic, which is much stricter. To prove a statement is true, it demands that you give it a direct, constructive proof. You can't just show that its opposite is false. You actually have to build the thing you're claiming exists. Now, I know this all might sound incredibly abstract, but this is the part of the story where we take a really surprising turn and connect this world of pure logic directly to the software we all use every single day. It might feel like a massive leap, but this deep structural analysis of proofs
led to one of the single most important insights in all of computer science. What is the real connection between proving a theorem and running a program? The answer is something called the Curry-Howard correspondence. It's this deep, kind of beautiful discovery that reveals there's a direct one-to-one mapping between mathematical proofs and computer programs. In a very real sense, they're the same kind of object. Here's kind of how the dictionary works. A logical statement, a proposition, corresponds to a data type in a programming language. And a proof of that proposition, that's a program, a function, that returns a value of that type. The assumptions are the program's inputs, the conclusion is its output, and that whole process of cut elimination we talked about, that's literally just running the program. Just think about how powerful that is. It means a logically perfect proof is the exact same thing as a perfectly written, totally bug-free program. And this isn't just a cool thought experiment. This is the foundation for modern programming languages and the verification tools that prove that critical software, like in an airplane or a hospital, is absolutely correct. So after our whirlwind tour from Hilbert's crisis all the way to modern computation, what's the big picture here? Proof theory is literally the study of the grammar of our own reasoning. It gives us confidence in mathematics. It gives us the tools to build and understand new kinds of logic. It underpins the reliability of all our software, and it reveals this profound, beautiful connection between the act of proving and the act of computing. Which brings us to one last, pretty provocative thought to leave you with. If the very structure of our logical arguments can be mapped directly onto computational processes, what does that imply about the nature, and maybe even the boundaries, of human knowledge itself?